Well, welcome back, everybody. And this is our second last week. And the topic today is again this Lagrangian formalism. And we are going to try to catch many birds with just a stone, in the sense that we want to both introduce examples as a way to repeat what we have done. And then at the same time, we're going to show how you can use this Lagrangian formalism to actually set up the equations of motions. And it's an extremely powerful way of getting to the equations of motions. When we have the equations, obviously at the end, we have to solve them. So this Lagrangian formalism starts with the energies and gives us the equation of motions, but it does not mean that it solves the equation for us. So we have to do them at the end. And I'm gonna bring in also examples from this coming homework. There's an exercise 5, which I'm going to go through some of the details. And you will also see that in some of the exercises, there are quite some elements of repetition. This week, the exercises are mainly paper and pencil. On the final, you will encounter something about the Lagrangian formalism. So this is not a mean way of me to sneak in the attention in class so that you have to pay attention because you will encounter something similar. But it's a part of the topic of the course here. And you may encounter some of these examples in the final, but these could also be examples which you've seen before. I actually had a funny teacher when I took mechanics, and this person was actually pretty funny. And he also took the consequences that he was not an optimal teacher. So he would always, everybody knew that the last lecture, he would go through the final exam. And then the final exam would just be a small perturbation of what we saw in class. I'm not going to do that. This guy actually had a funny exercise once. This is a legend, but we had 2 big towers, and the people teaching mechanics were on the top tower. And I don't know whether he was quarreling with another professor, but he gave an exercise which was how to throw Professor X out of Professor Y's window and make it look like as if he fell out of his own window. So according to legend, that was an exercise which was given in a mechanics class. I think it's pretty, the guy was pretty funny. Anyway, let's go back. So I'm mainly gonna use the whiteboard today and go through various examples and also link it up with the homework we have. And for those of you who wish to hang around, we have this room available till 5 o'clock. And same thing with Friday. Friday, we're only going to dedicate time for the last homework. There is an additional homework 10 if you wish to do that one. Also for the final, since this room will be available, I thought to propose that we could, for those of you who want to come here during finals week and discuss the final exercise, we can meet at the same days as we have lectures, if that sounds okay. If it's of interest. I will be here anyway. Okay, so let me switch over to the whiteboard and try to go through some of the examples which we started to look at. So the example which we looked at on Monday was an example which we called a Lagrangian with constraints. And this is also a very powerful way of gaining and finding the equation of motions. And in our specific case, what we were looking at the last example, after we did the pendulum, we took this top-down approach where we started to use equation without having derived them. And we're going to do that today, by the way. So we can now set up a gravitational force, G, and then we have this object which is sliding on a plane here. And we have a constraint that it should stay on the plane. And there's an angle phi, or alpha as we called it. And the constraint now, which we put up, this Gx of y, was so that we had y minus x times tan alpha has to be equal to 0. And that follows simply from the fact that y divided by x is equal to tan alpha. So the angle alpha is kept fixed. And that means that the ratio between y and x is given by tan alpha. And this is a constraint which we put on the equation here. And then the Lagrangian, which we are going to look at, is a Lagrangian with a so-called constraint. So we would have 1/2, and then we have the velocity in the x direction, plus the velocity in the y direction. And then we have a minus m times g times y, plus this constraint lambda, which is multiplied with, so this is called a Lagrangian multiplier, which follows from the fact that x and y are not independent variable. If you fix x, you have y. And that reduces the number of degrees of freedom which we have. And we are going to, after this example, I'm going to derive this equation or this modified Lagrangian. And then what we end up doing then is simply to use the Euler-Lagrange equation. So we would have a dl d of x minus the time derivative of the partial derivative of this Lagrangian with respect to the velocity in the x direction. And we require that one to be 0 when we make a small modification in the x direction. And if we do the derivatives here, you see now that there is a dependence on tan alpha and this lambda. So when we take the derivative with respect to x, there is a term which comes from this function. And furthermore, there is no term here. So what we are going to have then is, for one of the equations, we are going to get, this one gives us minus lambda times tan alpha when we take the derivative. And the second one gives us simply the acceleration in the x direction. And that means that m times x, the second derivative, is given by lambda or minus lambda times tan alpha. And we know that this tan alpha is also given by y times x here, but this is given by tan alpha here. So that's one of the equations which we end up with. And then we can do the same thing with the Euler-Lagrange equations in the y direction, minus d dt. And then we have the derivative, the partial derivative with respect to the velocity in the y direction. And if I go back and look at the Lagrangian and take these derivatives, I'm going to get an equation which runs like minus, and I'm going to have m times the second derivative y with respect to time. And then actually I did something wrong. There should be a plus here. I see that now. And this gives us a plus m times y, I'm sorry, m times g plus this lambda is equal to 0. So I'm taking the derivative with respect to y, and I have a term here which goes like lambda times y, and multiplied with, so we have y minus y times lambda, and when we take the derivative of that one, we get this term lambda here. Now, what we can do now is also that we know that if we take this relation that y is equal to x times tan alpha, from this one, we know that since alpha is a constant, then we can take the second derivative on both sides. So that means that the velocity in the y direction is equal to the velocity in the x direction. Sorry, the acceleration in the y direction is equal to the acceleration in the x direction multiplied with tan alpha. And if I use that, and if I look at the equations now, I take the first equation which we have. So let's call this equation here, this one, for equation x. And then we have the next one as equation x here. And we can now multiply these equations, and this is a standard manipulation which we often do. So multiply the first equation with tan alpha. So what I get then is m times the acceleration in the x direction multiplied with tan alpha. And this is equal to minus lambda of tan alpha squared. And then I manipulate these equations. I subtract the next equation, subtract this equation here from that equation, which we have. And if I do that, then I can simplify things and I get the following. So I'm then going to get, if I do this subtraction, just setting up the answer here, it's not so exciting to go through all these details. This is going to be given by m, we remember that we have m times this derivative here, as we found. And we get an equation then which goes like lambda times tan of alpha squared plus lambda minus n times g equal to 0. And then what I find then when I divide with the tan alpha, I can now find an expression for lambda. So I will find that lambda is equal to n times g, and this is going to be given now by cosine squared of alpha, and I get a further equation where I have now x, the second derivative with respect to time for in the x direction, is given by minus g times sine alpha multiplied with cosine alpha. So these are just algebraic manipulations I end up doing. And finally, I have y, which is going to be equal to minus g times sine squared alpha. And again, what you see now is that this term here has a dimension of force. So this is actually the force which acts on this object, which is sliding down from so this would be actually the force which acts on this object from the incline which we have here. So if I now bring everything together, so this is a force. So the force on the object from the incline. And we can actually derive that one from the Lagrangian multiplier. If we do this now, we do the first integration with respect to time. And then we are going to get the velocities. So that means that we will get first the velocities and then integrate again. So we will get x and y. And finally integrate again, and then we have the final answer. Integrate again with respect to time. And what you will end up with then is the final answer, x of t, which is going to be given by some x of 0 plus some initial velocity, which is going to be given by x0 of t minus x0 is the initial position, minus 1/2 of g squared times sine alpha, and finally multiplied with cosine alpha. And finally, for y of t, this is going to be equal to y0 plus an initial position times time. So this is our initial velocity, v0x, and this is going to be v0 in the y direction. And this goes like minus 1/2 of g times t squared, and then I have a sine of alpha squared. So this is one of these cases by simple manipulations of the equations and using the Euler-Lagrange formalism that we can actually integrate up analytically. So this is a case where we don't need to do numerical work. And the only thing I did was simply to use the Euler-Lagrange equations, manipulate a little bit the two equations I get, and then integrate up twice. And then I have the final positions as a function of time. So this is a typical approach which you will encounter in many, many different applications. Now, what I have not given you is actually the derivation of these kind of Lagrangian multipliers. Where do they come from? So the question then is, how do we derive this additional term, which we call lambda times g of x of y? Actually, the derivation of this one is not that difficult, but I think it's important to have seen it so that this is not something which I'm pulling out of the hat and telling you that this is something you should add to the equation, because then you're going to get a much easier way to solve things with a constraint. So let's just go through the mathematics for this so that we have the full picture of these elements in variational calculus. And what I'm going to do now is just to go back to that simple case we had with a mathematical function. So the formalism which we deal with is independent of whether we apply this to physics or problems in economy or problems in machine learning, where we want to optimize something with a given constraint. So this is a pretty standard technique if you want to optimize a specific function with a given constraint. So if you think back to that example we had on Monday, so we had an example with a function. So we had a function x1 of x2 here, which we just cooked up on the fly. So this went like 3x1 minus 6x1, and then we had 5. Actually, this was not that function. Let me just write it. It went like x2 here, right? So let me just write it correctly. So it had an x2, a minus 5 x2 squared, plus 7 x1 plus 5 x2. And then we had a constraint. And this is normally called a holomonic constraint if you have a function equal to 0. And that was given by x1 plus x2 minus 5. So we are going to look at a function like that. So we defined a Lagrangian, which now contains this x1, x2, plus a lambda times g of x1 and x2. So the question now is, where does this guy here come from? And this is what I wanted to show you, how you can actually obtain that. So we want to minimize. This is a type of problem, either minimize or maximize a given function. We want to minimize this function x1 subject. And there's no problem actually in increasing this to many more variables. So when you've seen it for 2 variables, which are going to depend on each other, you will see that this is something you can generalize to many more variables. And that means that you're going to get many more of these constraints. So this is subject to this constraint. And this is normally satisfied by points on that line, as we saw on Monday. So this will be satisfied by some points, which I'm going to call x tilde, which are going to be given by some x1 tilde, and there's going to be an x2 tilde. So this represents the solution on that specific line. That's where we minimize it with that specific constraint. So one of the things we have when we do this kind of optimization, there's a necessary condition which we have to fulfill. So this is one piece of mathematics which we need. So we need to show that d of f has to be equal to 0 when this small line segments dx, this segment dx1, so let me mark it a little bit later here, plus df of dx2 of dx2 is equal to 0. So this line segment has to be equal to 0. And these two, dx1 and dx2, are actually on our small variations that are on the constraints. So these are points on the constraint which we have. So the next thing which we are going to do then is, again, to use our famous Taylor expansion. And we are going to look at an expansion around the minimum. So we have this x1 tilde, which is the solution we are looking after. And we have this dx1. We assume that these are very small. So this is a small deviation around the minimum value. And we want still this small deviation to be equal to 0. So we're going to Taylor expand that one. And when we Taylor expand it, so we want this to be like that. So what we obtain then is an dx1 and an x2 tilde plus a dx2 here. And that's going to be approximated, since we assume that dx1 and dx2 are very small. This is going to be approximated with a value at the minimum or the maximum, if we are maximizing, plus the first derivative with respect to x1, and then calculated at the values x1 tilde, x2 tilde, times dx1, plus this dg dx2, evaluated at the values x1 and x2 tilde, which are the values at the minimum, multiplied with dx2 here. So we are going to require that in our case, we require that this dg of dg dx1 of dx1 plus dg, the derivative of the function with respect to x2, that this one is equal to 0 at the point x1 tilde and x2 tilde. So that's a requirement which we have. We're also going to make an assumption now that this dg of dx2 here is different from 0. That's an important assumption. And if we now look at the equation which we have here, this specific equation, we want this to be 0. That gives us an expression for the partial derivatives. And we get then, if we use this requirement, then we have that dx2 here is going to be equal to minus dg of dx1 divided by dg of dx2 here, multiplied with dx1. So this is just a manipulation which we've done now in terms of these partial derivatives. And if we now go back to this equation d of f, which we also require to be 0, that's the total function which we now want to optimize. So at the minimum, it should be 0. This is now going to be given by d of f of dx1. And now I can replace this dx2 with the quantity which you see here. So I can actually rewrite this one in terms of minus dg of dx1 divided by dg partial derivative with respect to x2. And this is multiplied with df dx2, and finally multiplied with dx1. So this must be satisfied for all possible values of dx1. So it must be satisfied by all possible values of dx1. Now, what we don't know is actually what the value of some of these functions are. So what we do next is that we simply define a parameter lambda, which is equal to minus d of f of dx2, this partial derivative, divided by dg of dx2. So we actually take all the x2 dependence into this parameter. Now, the thing now is, since we have this constraint, x1 and x2 have a dependence upon each other. So when you fix one, you fix the other one. And this is exactly what we are doing now. We take all the x2 dependence and put that one into a constant lambda. And this parameter is called a Lagrange multiplier, because you multiply that one with the equation for dg of x with respect to x1 here. So what you get then is the following. When you collect everything, you have this one, you require that one to be 0. So this is the same as the partial derivative of with respect to dx1 plus lambda. And you see now that I'm left with this term here. So that means that I get a dg of dx1 multiplied with this d of x1. So this quantity which you see, this lambda, is called a Lagrangian multiplier. And if you now look at the equation here, that means that you can now define a new function, which I'm going to call a function f. So I'm going to define a function f prime, which is going to be given by the original function f plus lambda times g. And this defines now, if we now want to define this as a Lagrangian, so we could simply rewrite it as an f of x1 of x2, which is now equal to the original x1, x2, plus a lambda times this g of x1 and x2. So this calculus of variations, if we have some dependence among the variables, that means that some of the variables are not independent, then we can actually rewrite this Lagrangian in terms of a new function, which contains this parameter lambda, which we can actually tune in order to optimize the function. And this is called a Lagrangian multiplier. So this comes simply because we have these derivatives which involve x2, which are fixed in a way when we know x1, and we can simply replace that with a constant. And that's basically the mathematics behind this. And then clearly you can include more and more conditions. You can have a multivariable function, which depends on x1, x2, x3, and so on and so on. And then you can just keep going, and then you will have for every new variable, which depends on the other variables, you will get a new Lagrange multiplier. So when we now optimize with a constraint, what we are doing now is simply to find a function which has a specific constraint, and then multiply that with the unknown parameter, and then we optimize everything so that we can find this optimal parameter. And that's the basics of Lagrangian multipliers. And that's the way we implement the constraints in the derivation of the Euler-Lagrange equations. Any questions so far? Have you seen this in mathematics courses? I guess you've seen some calculus of variations in some of the courses. So this is, I just wanted to bring it up in case you have not seen it before. It's not that difficult to perform these derivations. Now you can have different types of constraints, but what I want to do now is actually to bring up more examples, because we are going to use this kind of examples in order to remind ourselves of things which we have seen before. And I wanted to bring up as a new example, exercise number 5, which we have in the present homework. And that brings back this Lennard-Jones potential. And I wanted to say something about that one as well, because it allows us to repeat a little bit about potential surfaces and what they actually mean. So let's bring that up, a new example. This is a case where we don't have a constraint. So we can actually use that potential here. So this will be example 5. Okay. So this is the exercise 5 in homework 9. And what we have is a potential which depends on this R, which is the relative distance, and it's the absolute value. There is a constant for epsilons. Sometimes you will see this just as a constant V0. And then the potential has a constant sigma divided by R to the power of 12 minus this sigma divided by R to the power of 6. And R, if we have two particles, is given by the relative distance between particle 1 and particle 2 here. So in the exercise, you actually asked to plot this function. No, you asked actually to go to relative and the central mass, relative coordinates and the central mass system, and then derive the force which acts in the relative coordinate direction. Now, if you now plot this force here, let me try to see if we can bring up some elements of repetition here. So if you make a plot, and in this case, we don't need the centrifugal barrier yet. So the potential is going to look something like this. And before we move on now, I wanted to ask you a little bit, what kind of physics would you expect when these are? So sigma is a positive constant. So sigma is larger than 0. And we can also look at this epsilon. We can have epsilon negative or positive. It doesn't matter so much right now because it's the radial dependence which is important. If you look at the first case and you let R be larger than sigma, which term in the potential will dominate? So if you think of the value of this potential and you look at the plot here, and you assume now that sigma is smaller than R. Sigma is a constant. This potential is not a fundamental force. It's actually a fit to collisions between different atoms. And it's used in calculations like molecular dynamics to actually simulate properties of materials. It can be used to simulate gases. It can be used to simulate phase transitions, etc., etc. So it's a very popular, some of you will end up doing material science, you're going to encounter potentials like this, which are fit to experimental data. So suppose now you have this fit and you would like to make some physics interpretations. And this is the kind of things which we typically always do. And if you now look at what we did in the second midterm, the first midterm, and many exercises, we've had such a potential surface. And then looking at the potential surface, we can say something about the motion. So what kind of physics would you expect if R is larger than sigma? Which term dominates? That's the first thing. Which term in the potential dominates then? So just give it some time and think about it. So which term in the potential would dominate when R is larger than sigma? Yeah?
Sigma over R to the 6th.
Say it again.
Sigma over R to the 6th.
To the 6th. So the question then, if that term dominates, which value will the potential take? Will it be positive or negative? Negative. What does that mean for the type of motion you can expect? If the negative term dominates. So think now it's the negative value. We have plotted 0 as the origin. So that means that you will be somewhere here, right? I'm going to wait I know you know the answer. Sorry, mate. So if the negative term dominates, what kind of motion would you expect? Yes, you can get an elliptical motion, or if you're at the bottom, it could be a circular motion. So by just looking at the potential here and say something about the terms, you can quickly say which term will dominate or not. So in that specific case, we have a term. So this is the sigma divided by R, 6 dominates. And that means that what we can expect something which would be bounded motion. This depends also on the kinetic energy. Keep that in mind. So it's not given that you will get bounded motion, but you could get it. And it depends on the kinetic energy. So this is bounded motion. That means it could be elliptical or it could be circular. So you could now think of placing yourself here, and that would be your energy. So that could give that specific case. If we go to the next case and we look at the R smaller than sigma, and then you look back at the potential here, which term is the one which dominates them? Yeah, the first one, exactly. So this means that we may actually get values of the potential which are positive. So which value does the kinetic energy take? I didn't hear. So can the kinetic energy be negative? So the kinetic energy is always a positive quantity because that's the mass of the object multiplied with the velocity squared. So that means that if the second term, no, the first term is the one which dominates, that means that you would have, you can get, because you could actually have a situation where you are here. But suppose now that you are here, so you would get that one. And so then in this case, it's the sigma divided by R over 12 dominates. So if I'm here, what kind of motion do we expect? If you think back to the two-body problem we had from the gravitational forces. This is a hyperbolic motion. You could also have a case where you have the energy equal to 0, and then you would get a parabolic motion. So you see now that the kind of things which we have with the gravitational forces are things which we may expect to happen here as well. Except that now there are two terms in the potential. So sometimes this potential fits. Remember now, this is not something which comes from a fundamental force. So we call this an effective type of potential, because what you have done is to look at, for instance, scattering between two atoms. And these atoms can contain many electrons and protons and neutrons, etc. So what we're actually doing now is to think of every atom as one object. They collide, and we reduce that to a two-body problem. So that means that in these parameters, what we have absorbed is a lot of complicated interactions between the various electrons, the protons, and the neutrons, etc. But a typical potential, like that one, is something which, both in classical physics, which we are dealing with here, or quantum mechanics, is something which is essential. So if you don't have a potential like this, you will not have a minimum. So not having a minimum means that you will not have an energy which saturates when you have many particles. It means also that you will not get bounded orbits. And that's very important. So any type of effective potential which acts between objects, either classical or quantum mechanical ones, needs to have a balance between this repulsion, where the potential is positive, and the attraction, where the potential is negative. And that is needed in order to have a bounded motion. So that's a very important feature, which you will see again and again, in particular when you do quantum mechanics, but it applies to classical mechanics as well. So that was a little bit, a small element of repetition. Now, when you look at this potential here, without having done any calculation, and let me now set it up here, and this is the same as curl of minus the gradient of the potential with respect to R. What would you expect this one to be for a potential like this one, without having done any calculations? So this is again an element of repetition here. So if I calculate the curl of the force, and I have a potential which depends only on the radial distance. It depends only on the spatial degrees of freedom. What does your intuition say now, after having been here for, it's now the 14th week for you guys? You've been extremely patient. So what would you expect for the curl here, if you calculate for this potential? If you think back about the gravitational force, what was the curl of the gravitational force? 0, exactly. So with a potential like this one, if you now calculate the curl, without us doing it now, because this is not a very exciting exercise, it's going to take some 5-10 minutes by just boring derivations, you're going to get 0. So this is actually an example of another conservative force. It's an effective force because it's not based on a fundamental theory. So the gravitational force is seen as a fundamental force for the interaction between two objects. like the strong force or the electroweak force, are also examples of fundamental forces. This is an example of an effective one. So what we could do next is, obviously, if you now think of this specific force, what do you think you should get for this quantity? Without having done any calculations. It depends on the relative distance now, right? So since it depends on the relative distance, it means, so remember now that this is the same as a derivative with respect to time of r cross p. And we found that this is something we could rewrite as r multiplied with a force. R is the relative distance now, keep that in mind. So R is R1 minus R2. And when we calculate this, the force here, which is the gradient of the potential, we are going to get something which will depend on the absolute value of the distance times R. This is a typical example of the type of forces which we encounter for the interaction between two objects. So if you have these quantities, what would you expect for the angular momentum and its derivative as a function of time? 0. So angular momentum is constant. And you will find the same thing, since these are internal forces only. When we now sum all the internal forces, the one which acts on object 1 from object 2, plus the one which acts on object 2 from 1, they're going to have the opposite signs, and they will cancel each other, which means that the linear momentum will also be conserved. So these are examples, again, of things which we have seen throughout the semester. So the thing which we are going to do next is actually to use this Euler-Lagrange equations and find the equations of motion. So we are simply now going to set up a Lagrangian, which is going to be given by 1/2, and then I have the relative and the reduced mass. We have a v x squared plus a v of y squared. And then we have minus the potential energy. And this potential energy is the one which we have in these equations here. So that means that when we now want the equations of motions, what we need to do is actually to make a transformation to polar coordinates. And this is one of the parts of the exercise. And in the exercise, you're reminded to actually find the expression for the kinetic energy in polar coordinates. And let me quickly remind you of that. So x is going to be given by r times cosine phi, and y is again r times sine phi. And we know that x and y, they take values from -infinity to +infinity. R, when we make the transformation, goes from 0 to infinity. And then we have the angle phi, which is defined from 0 to 2 pi. So this is also another element where you're tasked in the homework to show that you can actually rewrite the kinetic energy, which now is written in terms of the velocities in the x and the y directions, in terms of the velocities in the radial direction and the angular velocities. So this is going to be given by mu here, and then we have r dot squared plus r squared times phi dot squared, like that. So now, when I want the equations of motions, the thing which I'm going to do is actually to take the Euler-Lagrange equations and apply them to the system here. And then instead of doing all these heavy exercises we did when we derived the two-body equations, we are now simply going to use the Euler-Lagrange equations, and we are going to take the derivative with respect to r minus d dt of dl of d of r, and this is equal to 0. Now, if we now go back to the equation for the potential, you see now that the smart thing with going to polar coordinates is that now we can, it's easier, it's not so exciting, but it's a little bit easier to calculate this derivative with respect to r. So we have a dependence on r here and a dependence here. So that is going to give us now a following term. When I take the derivatives, I'm going to get a term which goes like 24 times this parameter epsilon. And I think, let me see that I put it in correctly here. Yeah, 24 times epsilon. And then I'm just going to pull out sigma squared. And then I have a r to the power of 7. And then I get -2. So this is a derivative with respect to r. And that takes place in the potential here, divided by r to the power of 6 plus 1. So that's a derivative of the potential with respect to r. And then I get an additional term, which goes like plus mu times r multiplied with the angular velocity squared, minus, and then I have the second term here, which gives me this one. So this is going to be minus mu times the radial velocity. And if I plug in, if I reshuffle things and divide by the mass here, I'm going to get the acceleration in the radial direction, which is given by r divided by phi squared, which actually is going to be proportional with the angular momentum, plus 24 times this epsilon. And then I'm just going to rewrite it a little bit. I'm going to put a mu over r here. And then I bring back the term like this to the power of 12 minus sigma divided by r to the power of 6. So this is our acceleration now. So if you want to program this, what you need to program, and we know that the angular momentum is conserved. So that means that what we have here, if we now remind ourselves about phi dot, that is given by L divided by mu times r squared. So I could actually plug that one in here. And then I will get a term which goes like r to the power of 3 times the angular momentum squared, which we have seen before. So the difference now compared with the gravitational problem is that we needed this angular momentum term to get this potential, which looks like the Lennard-Jones potential. Now, this comes on top of the Lennard-Jones potential. And depending on the value of the angular momentum, you can get a potential which becomes more repulsive or stays pretty close to what you have in the expression from now. So this angular momentum term will change a little bit. But what you see is that this is a typical case of something which you cannot solve analytically. So here you would have to calculate everything numerically and integrate up the way you did in the second midterm. And then you can do the same thing and obtain the equations for the angular velocities and the angles. So if I take the next step, then I would have a d of L of d of phi minus d dt of d of L of d of phi dot. And this is going to be equal to, when it is equal to 0. The first term, there is no phi dependence in the potential. There's no phi dependence in the Lagrangian. The only dependence on phi is on the angular velocity. So if I plug in that one, this is going to be equal to minus mu times r squared times phi second derivative. And we know that this term, which we have here, is a term which we then can relate again to the angular momentum. But what it means now is that in essence, what we have is that phi is going to be equal to 0. So that means that the total angular acceleration is a constant, now is 0, which means that when we integrate it off, it means that the angular velocity is going to be 0. So this is an equation which is easy to solve. And the problematic equation is the one which involves the radial degrees of freedom. So here, we would have done the same thing with a gravitational force, except that now we have a slightly more complicated interaction or potential. But still, the kind of equations which we get are the kind of equations which we can actually plug in a numerical program and then solve the equations in the same way as we solve the Earth-Sun case. And you see also that with this type of potential, which you have, you can now define a system with many particles. So this would be like the planetary motion which you had, where you added the force from every planet to Earth, to Jupiter, etc., etc. Now, if you have many particles here, every particle would see a contribution from the force coming from all the other ones. So this would now represent just the motion in the relative degrees of freedom. If you want to program this, you would have to find the forces and the accelerations for each individual particle. And that's what we would program. And that would be, if you have many particles, it will simply be the sum of the contributions of the forces from all the other ones, like you did for the solar system. So you see the kind of pattern. This was actually, I see Abby is here now, so this was actually the part of the final last year, which means you will not see this in the final this year. But we are going to look at some of these calculations next week as well, and how we can solve them numerically and not analytically, but numerically. So it's pretty close to what you did with the solar system. With a code for the solar system, you can actually solve many other types of many body problems, as long as you know the potential and the forces. Okay, I'm gonna stop here. I went a little bit over time. If you wish to hang around and discuss the solution of the last homework, feel free to hang around. And if not, yeah, just gonna switch here. So to those of you online, I'm going to stop the recording.